Every fundamental interaction, from a proton's ephemeral dance to a galaxy's stately spiral, adheres to an ironclad set of rules. We perceive randomness in the fall of a die or the decay of a quantum particle, but even these probabilities are governed by precise equations. The universe doesn't roll dice, it executes algorithms. We often speak of quantum uncertainty, the inherent probabilistic nature of reality at its smallest scales. Yet, this randomness is itself a highly structured, statistically predictable phenomenon. It's not chaos, it's a specific order. Consider the conservation laws: energy, momentum, charge, and fundamental constants like the speed of light or Planck's constant. These aren't suggestions, they are inviolable commands etched into the fabric of space-time. A particle spontaneously gains energy. A photon always travels at sea in a vacuum. These are the rules of the game, a grand self-assembling clockwork. If the universe's deep structure is so utterly non-random, does genuine free will even exist? Or are we merely complex computations following an inescapable cosmic code? This isn't just a philosophical musing, it is the bedrock conclusion of centuries of physics. The universe at its core is a bookkeeper of almost unimaginable fastidiousness. Let's start with the most fundamental of these rules, the conservation laws. They are the non-negotiable statutes of existence. The law of conservation of energy states that the total energy of an isolated system remains constant. It can be transformed from one form to another, from potential to kinetic, from mass to energy as described by Einstein's famous E=mc². But its total sum is never created or destroyed. When a star explodes in a supernova, unleashing more energy in seconds than our sun will in its entire lifetime, not a single joule of that energy is new. It was all there before, locked away in the star's gravitational potential and nuclear fuel. The universe simply balanced its checkbook. Every single particle collision recorded at CERN's Large Hadron Collider confirms this. Physicists meticulously sum the energy and momentum of all incoming particles and compare it to the total energy and momentum of the debris flying out. The numbers always, without a single documented exception, match perfectly. Then there is the conservation of momentum, which dictates that the total momentum of a system remains constant if no external forces act upon it. This is why a rocket moves forward. By expelling mass backward, the total momentum of the rocket plus exhaust system is conserved. It's why a rifle kicks back against your shoulder. On a cosmic scale, it's why galaxies spin and planets orbit with a clockwork predictability that allowed us to plot their courses centuries before we could ever visit them. And it goes deeper. Conservation of angular momentum ensures a spinning ice skater speeds up when she pulls her arms in. It also ensures a collapsing cloud of interstellar gas will spin faster and faster, flattening into the protoplanetary disks from which solar systems are born. Without this law, the structured spinning architectures of galaxies and solar systems would be impossible. And let's not forget the conservation of electric charge. In any interaction, the net charge before and after is identical. When a high-energy photon transforms into an electron-positron pair in a process called pair production, it creates one negative charge and one positive charge. The net charge remains zero, just as it was for the neutral photon. These laws aren't just convenient observations, they are absolute. But are they absolute? Where does this tyrannical order come from? The answer is one of the most beautiful and profound insights in all of science, discovered by the brilliant mathematician Emmy Noether in 1915. Noether's theorem reveals a deep, unbreakable connection between conservation laws and the symmetries of the universe. A symmetry, in physics, is a feature of the system that remains unchanged under some transformation. For every continuous symmetry in the laws of physics, there must exist a corresponding conservation law. The fact that the laws of physics are the same today as they were yesterday, a symmetry in time, is the very reason energy is conserved. The fact that the laws of physics are the same here as they are in the Andromeda galaxy, a symmetry of translation in space, is the reason momentum is conserved. The fact that the laws of physics don't depend on which direction you're facing, a rotational symmetry, is the reason angular momentum is conserved. These laws aren't arbitrary. They are direct consequences of the fundamental character of space-time itself. The universe conserves these quantities because its very fabric possesses a deep geometric uniformity. This is the antithesis of randomness. It is pristine mathematical order. Now you might argue, what about the quantum world? Isn't that the one realm where true, irreducible randomness reigns? The heart of quantum mechanics, after all, is the Heisenberg uncertainty principle and the probabilistic nature of the wave function. It's true that we cannot simultaneously know a particle's exact position and exact momentum. It's true that when we measure a quantum system, the outcome is probabilistic. An atom of uranium-238 might decay in the next second, or it might sit there for another billion years, and we can only ever calculate the probability. But this is a profound misunderstanding of what quantum randomness means. The randomness is not chaos. It is, in fact, governed by one of the most rigidly deterministic equations in all of physics, the Schrödinger equation. This equation describes how the wave function of a particle, a mathematical object containing all the information about its possible states, evolves over time. And its evolution is perfectly flawlessly predictable. The wave function moves through its space of possibilities with the grace and precision of a planet in orbit. The randomness only enters the picture when we, the observers, force the issue with a measurement. At that moment, the wave function collapses into one of its possible states, and we can only predict the odds of each outcome, as given by the Born rule. So, while the outcome of a single measurement is uncertain, the statistical distribution of millions of measurements is perfectly predictable. This isn't the lawless chaos of a Las Vegas casino. It's the highly structured statistical order of an insurance actuary. The rules of the game are fixed. The probabilities are non-negotiable. So, when we look at the universe, from the symmetries of space-time to the deterministic evolution of the quantum wave function, we see a system bound by an inescapable logic. The laws of physics are not suggestions. They are the source code of reality. Every event that has ever happened and ever will happen is an unfolding of these initial conditions according to this rigid set of rules. This leads us to a dizzying and perhaps unsettling conclusion. If the state of the universe at any one moment is a direct and complete consequence of its state the moment before, all the way back to the Big Bang, what room does that leave for anything else? If every particle, every atom in our brains is simply following these inviolable physical laws, is our feeling of conscious choice, of free will, nothing more than a grand, self-assembling clockwork? From the micro rules that govern every particle, we zoom out to the macro architecture of existence. The answer to whether we are living in a deterministic clockwork lies partly in an even more profound mystery, one that suggests the rules themselves were chosen with an almost impossible precision, the cosmic fine-tuning problem. The values of the fundamental constants of nature, the precise strength of gravity, the charge of the electron, the mass of the Higgs boson, appear to be exquisitely calibrated for the emergence of complex structures like stars, planets, and life. If you were to randomly dial these cosmic knobs, you would almost invariably produce a universe that is sterile, empty, and dead. Our universe is not just governed by laws, it is governed by laws with very specific and seemingly very fortunate numerical values. These values are not derived from first principles within our current theories, like the standard model of particle physics or general relativity. They are experimentally measured parameters that we must plug into the equations by hand. They are the fundamental settings of reality's operating system, and the evidence for their fine-tuning is written in the sky, in the stars, and in the very atoms that make up our bodies. Let's consider just a few examples of this cosmic knife edge. Take the strong nuclear force, the force that binds protons and neutrons together to form atomic nuclei. Its strength is about 137 times that of electromagnetism. If the strong force were just a few percent weaker, protons could not overcome their mutual electrical repulsion to bind together. The only element in the universe would be hydrogen. No helium, no carbon, no oxygen. No stars beyond simple hydrogen gas balls. No planets, no chemistry, no life. Conversely, if the strong force were a few percent stronger, protons would bind so ferociously that nearly all the hydrogen in the early universe would have fused into heavier elements almost immediately after the Big Bang. Stars as we know them, which are long-lived hydrogen-fusing engines, would never have existed. The fuel for life-giving suns would have been spent before the cosmic show even began. Our universe exists within this razor-thin sliver of possibility. Now, let's look at the balance between gravity and electromagnetism. Gravity is astonishingly weak compared to the other forces. The electromagnetic repulsion between two protons is about 10 to the 36th times stronger than their gravitational attraction. This immense disparity is crucial. Because gravity is so feeble, it takes a vast collection of matter, an entire star's worth, for it to overcome the other forces and ignite nuclear fusion. This is why stars are so enormous and, more importantly, so long-lived. They burn through their fuel slowly and stably over billions of years, providing the long, stable energy output necessary for life to evolve on orbiting planets. If gravity were significantly stronger, stars would be much smaller, much hotter, and would burn out in a few million years, long before complex life could ever get a foothold. The universe would be a flickering gallery of brief, violent stellar flashes instead of a home of enduring suns. Perhaps the most staggering example of fine-tuning is the cosmological constant, the term in Einstein's equations that represents the energy density of empty space itself, what we now call dark energy. This is the force driving the accelerated expansion of the universe. Our best theories of quantum physics predict a value for this vacuum energy that is catastrophically large. The theoretical prediction is off from the value we observe, measured by studying distant supernovae and the cosmic microwave background via missions like the Planck satellite, by a factor of 110-12. That is a 1 followed by 120 zeros. This is widely considered the worst theoretical prediction in the history of physics. To have the universe we see, the bare value of the cosmological constant must have been set at the beginning of time to a negative value that cancels out the enormous quantum contributions with an accuracy of 120 decimal places, leaving just the tiny positive sliver we measure today. If it were even slightly larger, the universe would have expanded so rapidly that gravity never would have had a chance to pull matter together to form galaxies, stars, or any structure at all. The cosmos would be a thin, featureless, and eternally empty soup. The very existence of galaxies is a testament to this unbelievable cancellation. This implies a universe not just laws, but utterly defined by them. The tyrannical architect we spoke of isn't a conscious entity, but the inherent, unyielding nature of these laws and their specific numerical values. They don't merely guide reality, they reality's blueprint. So, what are we to make of this? How did we win this cosmic lottery against such impossible odds? There are two leading and wildly different speculative answers. The first is the anthropic principle, often paired with the idea of a multiverse. This hypothesis suggests that our universe is just one of an infinite, or at least vast, number of other universes, each with different physical laws and constants. In this cosmic landscape, universes are constantly bubbling into existence, and the values of the constants are shuffled in each one. The vast majority of these universes are sterile wastelands. We, by definition, find ourselves in one of the rare universes where the constants happen to fall within the narrow range required for conscious observers to evolve and ask the question. There is no fine-tuning. There is only a selection bias. We are here because we couldn't be anywhere else. The second possibility is even more profound. It is the hope that the constants are not random at all. This line of thought posits the existence of a deeper, more fundamental theory, a theory of everything, that will one day explain the constants must have the values they do. In this view, there is no lottery. The strength of the strong force, the mass of the electron, and the value of the cosmological constant are not arbitrary numbers, but are instead mathematically necessary consequences of a more elegant and unified physical principle, much like the ratio of a circle's circumference to its diameter. Physicists pursuing theories like string theory or loop quantum gravity are, in essence, searching for this ultimate meta-law. They are searching for the equation that proves our universe is not just one lucky roll of the dice, but the only way a consistent universe be. This leaves us standing at the ultimate frontier. Is our existence the result of a statistical accident in an infinite multiverse, a fluke of cosmic chance? Or does the exquisite fine-tuning of reality whisper of a deeper, undiscovered order, a final theory that dictates the very parameters of existence, making our seemingly random universe the only one that was ever truly possible? The answer awaits us, hidden in the fabric of the cosmos.